In this series of lectures, we introduce some basic and important concepts in calculus. As an entry-level course, we often adopt approaches that are intuitively clear, but might not be mathematically rigorous. In particular, we will not use the famous epsilon delta language. Now, in this lecture, we'll look at another very important technique in computing integrals. It's called integration by parts. Now, let's see, what is the integration by parts? Which is basically the product rule. Okay, so from the product rule, we know, suppose f and g are two differentiable functions, right? And then the derivative of f times g equals the derivative of f times g plus the f times the delta of g, right? So this is the product rule. Okay, now you see, then if I take the antiderivative on both sides, now the antiderivative, if I have a function, right? If I say, okay, if function, the antiderivative of the derivative, now, of course, it's just the function itself, because the derivative of this one is just the derivative, right? Okay, right? Well, so this is equals the f plus c itself. Then, if you look at the left-hand side, it's just fg plus c, and this will be the antiderivative of L prime g, and this will be antiderivative of fg prime. Now, of course, you move this one to the left-hand side, and then you move this one to the right-hand side, and this is the more general form we write to express the integration by parts for antiderivatives. And here we omit the constant c because the constant c can be contained here and here, so there's really no need to write the constant c. Now, we use the antiderivative based on indefinite integral, but if you use that integral, it's the same thing, right? Let's do it here. If I have fg prime equals L prime g plus fg prime, if you say, okay, let's take the integration from a to b, dx, I take the integration of b and dx, the integration from a to b dx. Now, for this one, you can just apply the Newton-Raphson formula because it's a derivative, right? Okay, so this we know it just be the fg evaluated at two endpoints, take the difference, which is right here, right? And this one will, okay, it's just a to b and L prime dx, and this equals plus the integration from a to b and fg prime dx. Now, you just move, all right, so again, you move this one to the left, right, and you move this one to the left. And this is the form of integration by parts if we go with definite integrals. Okay, now let's apply this formula. First example, let's look at is we want to calculate this one. Okay, so I want to calculate the integral from 1 to 2 and log x and dx. Now, say at this point, we're not so clear what is the antiderivative of x is, right? Okay, so how should we use? Now, log x, I can write as 1 times log x. And what is 1? 1 is the derivative of the function x. So in other words, I can write this as derivative of fx and gx. For here, my fx is x, my gx equals log x, right? Equals log x. And then we can apply the integration by parts, right? So it's 1 times this. We say, okay, this is just equals the f times g evaluated endpoints and minus this f2 and this f times g prime and dx. Now, for this case, the g prime will just be 1 over x, right? 1 over x, and this f is x, and this is x. Now you see here the reason why we choose log x to be gx, because when you take the derivative, you get something which is nicer, which is 1 over x, right? Okay, so then let's put this, so the x times log x evaluated 1, 2, and then minus from 1 to 2, and here's x times the derivative is 1 over x dx. Okay, so you just cancel, get a 1. All right, and you plug this, so 2 times log 2, 1 times log 1, but which is 0, so it's which is minus 1. So it's 2 times log 2 and minus 1. Now, similarly, we can get the antiderivative. So if you get the antiderivative by the same way, we'll just get this. Okay, so this will just be x times log x, and minus the antiderivative of x times 1 over x dx, but this is 1. And the antiderivative of 1 is x, right? So, okay, so this is x log x minus x and plus constant. You can double check. It's okay, let's see whether it is indeed true. The derivative of this one is equals to log x. Well, let's check this. You can use the product rule. So it's okay. So if you take the derivative of this one, use the product rule, is log x and plus x times 1 of x. It's okay. It's log x plus 1, right? Okay, so it's log x plus 1. And then minus the 2 is 1. Okay, so indeed, it's log x. Okay. We can do you can also do when you have x in front of 8. Okay, let's just do this. This one you can do by yourself. It's very similar. Okay, so let's do this. All right. Say we want to find the antiderivative of x times log x dx. Again, we say, all right, we just apply the same thing, right? So what's the x? This is 1/2 x squared, take the derivative. So in other words, for this case, I take fx to be x squared over 2 and gx to be log x, okay? And then by the integration by parts, right? So again, we by integration by parts, we have this one, which is 1/2 x squared times log x and minus, this is 1/2 x squared times the derivative, so that will be 1x. So this is fx, this is the derivative of gx and dx, right? Okay, that's what we have. So we get is 1/2 x squared log x and minus this is 1/2 and x dx. Okay, so this will be 1/2 x squared log x, and this will be antiderivative of x squared, so it's x squared over 4 and plus some constant. And then you can double check. Let's say, okay, let's double check. Is it true? So okay, let's double check. Is it true if I have 1/2 x squared log x, right, and minus x squared over 4? If I take the derivative, 1/2 x squared log x, if I use the chain rule, right? If I use the chain rule, so this will be x log x and plus 1/2 x squared times 1 over x. So I get this x log x and plus x over 2. Now, if you take derivative of this, you get x over 2. So they cancel with each other. It will leave us with the x times log x. So which is indeed correct. Okay. Now, of course, then if you get this, then we know if you just want to get this, okay, I want to get x log x dx, right? You just use this antiderivative square log x minus x over 4, and you evaluate at 2 endpoints, and you take the difference. Okay. All right, let's look at one more. I want to find the antiderivative of x times cosine x dx. Here, let's see. We can choose, you can try a different way to see which one work for you. So for here, I say, okay, maybe I can use this as, because sine x, the derivative equals cosine x, right? So I choose fx to be sine x, and I take gx equals x. Now, why do you do that? Oh, that's because if I take the derivative of x is 1, this supposedly is going to simplify the integral, right? Okay, so then this one equals, which okay, so this equals prime g and dx. We apply this, we apply the integration by parts, so this is minus, then fg prime dx. Okay, so let's plug into everything here. So you get x cosine x dx. This will be f is sine x, right? And times g will be x, right? G to x, and minus f is sine x, g to dx. Okay, so then we need to find the antiderivative of sine x dx. Now let's recall that cosine x, when you take the derivative of cosine x, this is negative sine x. Okay, so that means the derivative of negative cosine x is sine x. Okay, so this tells us the antiderivative of sine x equals negative cosine x and plus some constant, right? All right. And then what we have is this equals to x, right? It's right here, and times sine x and minus cosine x and plus some constant. Okay, so then what we get is x times sine x and minus you get plus cosine x and minus constant c. Now this minus constant c you can also write as plus constant. This doesn't matter because c just represents an arbitrary constant. All right. Therefore, our answer, this one is equals x times sine x and plus cosine x plus constant c. All right, let's double check this to make sure that everything is correct. All right, so here we have x sine x, right? And plus and cosine x, cosine x. Let's take a derivative to see whether this is equals x times cosine x. Okay, let's see. So x times sine x, we take the derivative, we get using the product rule, right? And this we get a sine x and plus x times the derivative of sine x with cosine x. Okay, and cosine x, when you take a derivative, this is negative and sine x, and therefore, if you would do the addition, or you add them together, and x sine x cancel with sine x, and indeed, we get the derivative is x times cosine x. Okay, so it's correct. All right, now let's look at the last example. Here, what we want is we want to find the antiderivative of ex and sine x. So let's see which one should we choose as f and which one we can choose as g. All right, here actually either way, you can choose either ex or sine x to be fx, doesn't matter. Let's say I choose ex to be fx. Okay, so I choose fx. I choose fx to be ex, right? And then we know the derivative of ex is just itself, right? So the antiderivative of ex dx, again, is just ex plus constant. And I take gx equals sine x. All right. And then, of course, the g prime x will just be cosine x. Okay, so then this one equals, and we can, let's reply the formula using integration by parts, okay? This one will just equals the antiderivative of L prime and g dx, right? By the formula, this equals f times g minus then f times g prime and dx. All right, let's plug everything into the formula. And this is fx is ex, right? Let's recall this. Fx is ex and gx is sine x. Okay, so let's replace f by ex and g by sine x. And then minus the antiderivative, and f is ex and g derivative, right? G derivative is cosine x. Okay, so replace this cosine x and dx. Now at this point, you say, hey, but we still haven't got what we want, right? Because it is unknown what is the antiderivative of ex times cosine x, right? The trick here is let's do one more time. Okay, let's apply the formula. Okay, so the formula to ex times cosine x. Okay, so let's do. So we do again. We apply this one to here. Okay, so let's do it one more time. So it's ex times cosine x dx, right? Again, now this we apply this. So this will be my f prime. Okay, so we apply the formula to this. So this will equals the f. This is the f, right? This is the new g. So this is the new g. So f times sine x and minus the antiderivative of the f times cosine x derivative dx. Now let's recall, we say, okay, we know the cosine x, if you take the derivative, is negative sine x, right? Okay, so let's see what we get. Okay, so we get this will be f times cosine x, and this equals negative sine x. But then you see, you have this is negative, this is negative. So what you get is positive, right? So negative is positive. So it's plus this this is f times sine x and dx. Now let's just put this one back, right? So fx, let's recall, this is just ex, this f is ex. Okay, so let's put this one back to here, replace this term, right? So this term replaced by this. Okay, so what do we get? Let's see what do we get. And then this is equal, right? So okay, from here, this equals ex times sine x, right? And minus ex times cosine x, and then minus the antiderivative of f sine x and dx. Let's replace f by ex, right? So this is ex. Okay, now this equals, and remember, these are the same, right? So we get this is exactly here. So we say, okay, so we get this e entitled ex sine x, you should put it here, it's right here. Okay, now you see on the right hand side, on the left hand side, we have ex sine x, right? Let me just write one more time. So we get the entitled ex sine x dx equals ex, right? Ex times sine x, right? Minus ex times cosine x and minus the ex times sine x and dx. Now you see, the point here is, although we don't get rid of this, however, right, this is different from what we did for the previous two examples. For the previous examples, after applying this indication by parts, and eventually we reduce something which is doable, right? Which is doable, like here we do that. But here we end up with something. When you look at this equation, you say, okay, but you still haven't get rid of this ex sine x. But the point is, they are the same, right? So, okay, they are exactly the same. It's just two copies. So if you move this to the left-hand side, you just get two copies of ex sine x and dx, right? Equals, this is ex sine x and minus ex minus cosine x. But here, because there's a constant, so you can put a constant back, right? Could put a constant back. Okay, all right. And then you can solve this simple equation, and this will be 1/2, right? Ex and sine x and minus ex and cosine x and plus constant c. Now, and then you just get the antiderivatives ex sine x and minus ex and cosine x and plus a constant divided by 2. But you can replace it, okay, constant divided by 2. But this you can also replace just by one constant. But again, keep in mind, c is not a specific constant. It's just notation to represent any constant. Right, so I can use c or minus c divided by 2 or whatever. It's just the same thing. It just means a constant. All right, again, so let's double check. Let's double check whether this is correct. Okay, so let's double check everything to make sure that this process it's correct. Okay, let's look at the derivative of ex sine x minus ex cosine x. Let's take the derivative of the whole thing, right? All right. Okay, so let's see. By the product of sine x, let's take the derivative of this. So this will be ex times sine x and plus ex times cosine x, right? And then I have ex cosine x, right? If I take the derivative of this will be ex cosine x, and then minus ex times sine x, right? Because keep in mind, the cosine x, again, we have to remind ourselves, this equals cosine x, and cosine x, you take the derivative, is negative sine x, right? Okay, and then if you take the difference, okay, I take the right because I different here, take the difference, then you see this will just, this, not here, this one, this will cancel with this, right? So they cancel with each other, okay? And what you left is two copies of ex. This is plus, this is minus, you can take minus, minus, plus, and sine x, right? And then you see, if you take the 1/2 of the whole thing, 1/2 of the whole thing, we get is exactly ex times sine x. So everything is correct. Right. Okay, so the final answer here, this is what we get. Right? Put a constant. That's what we are looking for.